Imagine you just provisioned this massive multi-region database architecture.
Oh boy. I feel like I know where this is going.
Right. So you're setting up for an expected wave of Black Friday traffic. You've got red replicas in 3 different regions. Your auto-scaling groups are primed, and you hit launch.
And it runs flawlessly, I assume.
Flawlessly. You experience absolute zero downtime during the biggest sales event of the year. You go to sleep feeling like a total hero.
As you should.
But then 30 days later, your CFO calls you into their office, and they are just furious.
Because the AWS bill finally arrived.
Because the bill arrived, you accidentally burned like $80,000 in reserved instances that you didn't actually need. You effectively wiped out the profit margin for the entire quarter.
Ouch. Yeah, that is the exact nightmare scenario that separates the people who just, pass a multiple choice test from the people who actually know how to build in the cloud.
Exactly. And today we are going to make sure that never happens to you.
Because you can memorize all the technical definitions you want, but if you don't understand the underlying economic and operational mechanics, the cloud will penalize you heavily.
It really will. So if you are prepping for the AWS Certified Cloud Practitioner exam, the CLF-C02, or honestly, if you just want to survive your next architectural review board without getting laughed out of the room, you are in the right place.
Absolutely.
We are doing this deep dive just for you. Our mission today is to look past the endless forum dumps and completely deconstruct the fundamental why behind these core AWS concepts.
And we really need to set the stage by warning you about what I call the selected answer C phenomenon.
Oh, the forums are full of that.
It plays the public preparation boards. We've been combing through hundreds of crowdsourced exam questions, and the hive mind behavior is genuinely dangerous.
Yeah. People will encounter this highly complex architectural scenario, and the top comment is just someone saying, the answer is C, memorize it, and move on.
Which is a guaranteed recipe for real-world failure. Memorizing a letter without understanding the architectural trade-off is just, it's wild.
I saw one comment on a highly debated question that literally just said, I picked this one because it had the longest text.
That is terrifying.
Right, because these are the people who are going to be handed the keys to production environment.
Exactly.
So we are going to treat you like a peer today.
Yeah.
No dumbed-down definitions, no just, reading from the AWS glossary. We are going to connect the dots.
And to do that, we have to start at the absolute foundation. Before we even touch a line of infrastructure code, before we open the management console, we have to talk about why the cloud exists as a business model in the first place.
So we're talking about the economic shift.
Yes, the shift in business economics.
Because looking through our source stack, there is a relentless focus on the elimination of data center maintenance, the transition from CapEx to OpEx, capital expenses to variable expenses.
It's heavily tested for a reason.
But I want to push back on this a little bit, just to play devil's advocate. Hardware gets cheaper over time, right? Thanks to Moore's law.
Sure.
So if I'm running a predictable baseline workload, why wouldn't I just buy my own servers, treat them as a capital expense, and depreciate them over 5 years? Doesn't the cloud eventually cost more if you're just, renting forever?
That is the classic legacy IT argument.
Bro.
And honestly, it makes sense, but only if you isolate the costs of the raw silicon.
Okay, what am I missing?
A physical server doesn't operate in a vacuum. When you undertake a capital expenditure, a CapEx, you aren't just buying the server rack. You are buying the commercial real estate to house it.
Right.
You're signing multi-year contracts for industrial cooling. You're paying for redundant power grids, physical security guards, network engineers to run miles of fiber optic cable.
Yeah, all the hidden costs.
Exactly. Those are massive upfront sunk costs that require you to forecast your business needs 3 to 5 years in advance.
And if your business model pivots in year 2, you're stuck holding this multi-million-dollar bag of depreciating hardware that you can't easily liquidate.
That is the rigidity of CapEx. The cloud shifts that entirely to operational expenditure OpEx. You pay only for what you consume, down to the millisecond.
But wait, how does AWS make that OpEx model financially viable against depreciated owned hardware? Like, how are they actually making money if renting is so cheap?
Economies of scale. That's the secret sauce.
Because they're buying hardware at a scale that's incomprehensible to a standard enterprise.
AWS isn't just buying off-the-shelf servers from a vendor. They design their own custom silicon, like the Graviton processors. They negotiate power contracts for massive data centers at wholesale rates no single corporation could ever get.
Oh, wow. And they optimize everything globally.
Right. cooling efficiency, global supply chains. They take those massive operational efficiencies and pass the cost savings down to you in the form of lower variable costs. Your on-premises data center can just never compete with the sheer purchasing power of AWS.
So the economic shift is what actually unlocks the technological capabilities. And this brings us to a concept where the forms just completely self-destruct.
Let me guess. Agility versus elasticity.
Yes. The hive mind constantly conflates these two terms. They see the word scaling in a scenario and just smash the elasticity button. But elasticity isn't just a fancy corporate synonym for scaling up, is it?
It absolutely is not. Elasticity is a very specific technical mechanism. It's the ability to automatically right-size your infrastructure resources as demand shifts.
Okay, so acquiring resources when you need them for a traffic spike?
Yes, but crucially, and this is the part engineers often fail to implement correctly, it is the automated releasing of those resources when demand drops.
Let's drill into that release mechanism, because scaling up is easy, right? You hit a CPU threshold, your auto-scaling group provisions another EC2 instance, and the load balancer starts sending it traffic. Done.
Simple enough.
But scaling down without killing active user sessions or dropping database transactions, that requires some deliberate design.
Stateless architectural design, to be specific.
Because you say releasing resources like it's a simple toggle switch. But if my application stores session data locally on that server, releasing it means I just logged out thousands of angry customers.
That is a phenomenal point, and it highlights why elasticity requires architectural maturity. If you build a stateful application where the web server holds the session data in its local memory, you cannot safely terminate that instance.
You've basically handcuffed your own elasticity.
Exactly. To truly leverage the elasticity of AWS, you must externalize state. You store session data in a managed service, like Amazon Elasticache or DynamoDB.
Oh, so the compute layer becomes completely stateless.
Right. Once it's stateless, the auto-scaling group can terminate an instance at 3 in the morning when traffic drops, and it won't disrupt a single user. That termination is what stops the billing meter. That is the true financial power of elasticity.
So elasticity is the technical breathing of the servers, expanding and contracting.
I like that analogy.
Thanks. But if that's elasticity, what on earth is agility? Because the forum consensus always lands on the ability to experiment quickly. How does that differ from just spinning up a server fast?
Agility is not a technical scaling metric. It's a business capability. Think of agility as your organizational speed to market and your speed to innovate.
Okay, give me a real-world example of that.
Let's say your data science team has a radical new idea for a machine learning feature. In the old CapEx world, they would have to submit a purchase order for a specialized GPU cluster.
Right, and wait 6 weeks for the vendor to deliver it.
Have the infrastructure team rack it, configure the networking, install the OS. By the time they actually run their first Python script, the quarter is over, and your competitor has already launched a similar feature.
The friction of procurement basically kills the innovation.
Yes. But in the AWS cloud, agility means that same data science team can spin up a global GPU-backed architecture using an infrastructure as code template in 5 minutes.
They run their experiment that same afternoon.
And if the machine learning model fails to produce viable results, they just execute a teardown script. The infrastructure vanishes, and the company only paid for 3 hours of compute time.
Wow. So the cost of failure drops to almost zero.
Exactly. When the cost of failure is negligible, the organization is empowered to experiment constantly. Agility is the speed at which your business can move. Elasticity is how your technical architecture handles the traffic once the business launches the product.
That perfectly connects to the principle of stop guessing capacity, which is heavily tested. If you're an experienced on-premises architect, your entire career has been based on guessing capacity.
Usually over-guessing.
Right. You over-provisioned by 40% just to ensure you had headroom for unexpected spikes. Because running out of capacity meant the site went down and you got fired.
But in AWS, over-provisioning to ensure capacity is literally just setting your budget on fire.
It requires a fundamental unlearning process. You no longer need to predict the future. You build a stateless architecture, define your auto-scaling metrics based on actual utilization, and let the platform handle the variance.
You use elasticity to handle the spikes and agility to build the solutions in the first place.
Okay, so we have the financial model approved. We're using OpEx to drive agility and elasticity. We are ready to deploy. But the moment that first EC2 instance boots up, we hit this massive compliance gray area that trips up almost everyone on the exam.
Oh, the shared responsibility model.
Yes. The amount of confusion around this is staggering. There is this dangerous assumption among new cloud adopters that because they are paying AWS is inherently responsible for all of their security.
Right. If a server gets hacked, they assume it's an AWS problem.
Let's lay down the golden rule here. AWS is responsible for the security of the cloud, and the customer is responsible for security in the cloud. Let's define those exact physical and digital boundaries.
Security of the cloud refers to the foundational infrastructure. AWS is responsible for securing the concrete data center buildings.
The actual physical walls.
The walls, the perimeter fences, the biometric access controls for their employees, the redundant power supplies, the networking cables, and the underlying hypervisors that run the virtualization layer.
So if a bad actor physically breaches a facility in the Frankfurt region and steals a hard drive,
That is an AWS failure. If the Nitro hypervisor has a zero-day vulnerability at the virtualization level, AWS patches it globally without you ever even knowing.
but you, the customer, are responsible for what you put in the cloud. And this is where developers get lazy, honestly.
They really do.
You are responsible for your data, your applications, your guest operating systems, and your network configurations. If you provision a database and leave the security group firewall rules open to the entire public internet.
And an automated botnet scrapes all your customer data.
Yeah, AWS will not stalk you. They provide the lock, but you chose to leave the door wide open. That data breach is entirely your fault, both legally and architecturally.
And this is where the exam gets incredibly nuanced. The shared responsibility model isn't a single static line drawn in the sand. It's a sliding scale that shifts dramatically depending on the specific category of service you're using.
Let's start with the most basic compute primitive, Amazon EC2. This is Infrastructure as a Service, or IaaS. With EC2, you're just renting a virtual slice of a bare metal server, right? AWS hands you a virtual machine with an IP address.
Because it is infrastructure as a service, the burden of responsibility sits heavily on the customer. AWS provides the virtual hardware, but you choose the operating system, say Amazon Linux 2023 or Windows Server 2022.
And because I chose the OS and I hold the root SSH keys, I must patch that guest operating system.
Exactly. You must manage the application dependencies. You must configure the firewalls. AWS has no visibility into your EC2 instance. They cannot and will not log into your server and run a yum update or install Windows security patches for you.
I want to challenge this sliding scale model, though. Let's move up the stack to a managed service like Amazon RDS or DynamoDB.
Okay.
If AWS manages the underlying operating system on DynamoDB, how do I know they patched it correctly? Am I just trusting them blindly? Because in an enterprise environment, just trust us is not a valid compliance strategy.
You don't trust them blindly. You verify through compliance artifacts.
Artifacts.
Yeah, AWS provides a service called AWS Artifact. You can download third-party audit reports there like SOC2, ISO 27701, PCI DSS. Independent auditors verify that AWS is executing their end of the shared responsibility model.
Oh, so the proof is in the independent audit.
Exactly.
Yeah.
But to your architectural point,
Okay.
with a managed service like DynamoDB, do you have SSH access to the underlying server?
No. There are no SSH keys for DynamoDB. It's literally just an API endpoint.
Right. Because you do not have root access to the underlying compute, you cannot be responsible for patching it. The line of responsibility shifts. AWS assumes the burden of patching the DynamoDB operating system, updating the database engine, and maintaining the underlying storage arrays.
So what is left for the customer? If AWS is patching the OS and the database engine, what do I actually have to do?
You are still responsible for access control. You must use AWS Identity and Access Management IAM to explicitly define which users or applications are allowed to query that DynamoDB table.
Ah, so who gets to see the data?
Yes. You're responsible for classifying your data, enabling client-side or server-side encryption. AWS secures the platform. You secure how the platform is utilized.
And the line slides even further when we enter the realm of serverless computing, right? Like AWS Lambda. This is the ultimate abstraction.
With Lambda, you're moving from infrastructure as a service, past platform as a service, into function as a service. AWS maintains the physical hardware, the hypervisor, the operating system, and the computer language runtime.
So they make sure the underlying Python environment is secure and highly available.
Exactly.
But wait, I want to pause on that because there is a trap here. If I write a Lambda function in Python and I upload a zip file containing my code along with a bunch of third-party open source libraries I downloaded from the internet, who owns the security of those libraries?
I do. That is your deployment package.
Even in serverless.
Even in serverless.
Yeah.
AWS owns the security of the core Python runtime environment, but if you package a vulnerable version of a third-party logging library into your Lambda function and that library is exploited, that falls under your responsibility in the cloud.
So I still own the business logic.
You own your code, its dependencies, and the IAM permissions dictating what that Lambda function can interact with. The operational burden is drastically reduced, but your responsibility for the security of your code remains absolute.
That is a critical mental model to carry into the exam. Look at the access level. If you have root access to the OS, you patch the OS. If you don't, AWS patches it. But you always own your data, your code vulnerabilities, and your IAM policies.
Absolutely. And with that operational boundary defined, we need to talk about the actual compute engines, because this is where the massive financial mistakes, like that $80,000 bill you mentioned earlier, actually occur.
Oh, yes. The exam relentlessly tests your ability to match the correct billing model to the correct workload. Let's dive into the 2-month trap.
This one caused an absolute meltdown in the comment sections.
It did. The scenario is this. An e-learning platform has an application that must run for exactly 2 months out of the year to support a testing window. And the requirements explicitly state that any application downtime during those 2 months must be strictly avoided.
0 downtime allowed.
Exactly. And the forum, HiveMind, panicked at that phrase. They immediately started arguing that the correct answer was reserved instances. They equated the word reserved with guaranteed uptime.
And that is a perfect example of reading the English definition of a word, rather than understanding the AWS billing mechanism.
Break down the math for us.
Reserved instances, or IIs, are a financial commitment. You are signing a contract with AWS, promising to pay for a specific amount of compute capacity for a term of either 1 year or 3 years.
And in exchange for that lock-in?
AWS gives you a massive discount, sometimes up to 72% compared to the standard rate.
But let's look at the scenario. The application only runs for 2 months. If I buy a 1-year reserved instance to cover a 2-month workload,
you are legally obligated to pay for 10 months of compute capacity that is sitting completely idle.
oh, wow. So even with a 72% discount, paying for 10 months of dead air is going to cost vastly more than simply paying full price for just the 2 months you actually need.
The discount mathematically cannot cover the wasted spend. Therefore, the correct answer, despite the scary 0 downtime requirement, is on-demand instances.
Because on-demand lets you pay exactly for what you use, billed by the second, with 0 long-term commitment. And this is where the forum users got confused. On-demand instances do not randomly shut down.
Right. They are just as reliable and stable as a reserved instance.
You are simply paying the premium list price for the ultimate financial flexibility to terminate them after exactly 60 days. The phrase 0 downtime was a deliberate red herring designed by the exam raters to trick novices.
It tests whether you understand that reliability and billing are completely decoupled concepts in this context.
Now, if we look at a billing model where the instance can randomly shut down, we have to examine spot instances.
Oh, spot instances are fascinating.
I always explain them to junior developers by comparing them to flying standby on a commercial airline.
That's a great analogy.
Right. The ticket is incredibly cheap, you get a massive discount. But if a full-paying passenger shows up at the gate, or in the AWS context, if AWS needs that compute capacity back for an on-demand customer, you get bumped off the flight mid-air. AWS sends a termination notice, and you have exactly 2 minutes before the server is killed.
It's very accurate. Spot instances utilize the spare, unused physical capacity sitting in AWS data centers. AWS auctions this capacity off at steep discounts, up to 90% off the on-demand price. But as you noted, they retain the right to reclaim it.
Want to push back on the viability of this, though? A 2-minute warning is virtually nothing in the context of enterprise software.
It's very short.
If I'm running a massive Monte Carlo simulation for financial modeling and I get a 2-minute termination notice, I lose all my progress that was stored in the local memory of that server. How is that actually useful in the real world unless I am spending more time engineering the fault tolerance than I am saving on the compute cost?
You only use spot instances for workloads that are fundamentally stateless and fault-tolerant by design?
Okay, so no legacy monoliths.
Definitely not. You don't run a primary relational database on a spot instance. But for that Monte Carlo simulation, you architect the application to continuously checkpoint its progress to Amazon S3. Or you manage the individual simulation tasks in an SQS queue.
So if an instance is reclaimed, the task simply goes back into the queue.
Exactly. When spot capacity returns and a new instance spins up, it pulls the task from the queue and resumes from the last S3 checkpoint. The application architecture must anticipate and gracefully handle infrastructure interruption.
That makes total sense. It forces you to decouple the state from the compute. And speaking of decoupling compute, let's move into the serverless container space, because there's an interesting scenario here.
Fargate versus Lambda.
Yes, a company has successfully containerized their applications using Docker. They are currently running these containers on a cluster of EC2 instances, but the infrastructure team is exhausted.
I've seen this exact burnout so many times.
They are sick of managing the cluster sizes, patching the underlying host OS, and dealing with server maintenance. They want out of the EC2 management business entirely.
This is a very common evolutionary stage in cloud maturity.
Yeah.
They started by lifting and shifting their legacy code into Docker containers, which is a great first step. But running containers on raw EC2 instances means you are still managing infrastructure.
So what's the solution?
AWS Fargate. It is a serverless compute engine purpose-built for containers.
But wait, how does Fargate contrast with AWS Lambda? Because Lambda is defined as running code without provisioning servers. Don't both Fargate and Lambda do the exact same thing? If neither requires me to manage the underlying hypervisor, why use Fargate at all? Why not just put everything into Lambda?
Because they operate at completely different levels of abstraction and have very different execution constraints. Think of Fargate as serverless containers. You still build your custom Docker image. You still define the specific CPU and memory requirements for that container. But AWS provisions and manages the invisible underlying server cluster that runs it. You never see the EC2 instances.
But how long can it run?
Your container can run continuously for days, weeks, months. It is ideal for long-running microservices or legacy applications that require a specific container environment, but want to shed the server management overhead.
Ah, and Lambda has execution limits.
Exactly. Lambda is serverless functions. You don't have a container. You provide a block of Python or Node.js code, and you define a trigger like a new file landing in an S3 bucket.
And when the trigger fires...
AWS spins up the execution environment, runs your code, and then destroys the environment. Crucially, a Lambda function has a maximum execution time limit of 15 minutes.
15 minutes. So if I have a massive legacy backend process that takes 20 minutes just to initialize its connection pools?
Lambda will mercilessly kill it mid-execution. You need Fargate for that. The key takeaway for the exam is that both offload infrastructure management to AWS, but Fargate is the engine for long-running containers, and Lambda is the engine for short-lived, event-driven code functions.
So it's a spectrum of abstraction. You choose the primitive based on the constraints of the workload. You bring up legacy monolithic backends, which perfectly segues into how we actually blueprint these systems.
The frameworks.
Right. If you're going to use these compute primitives effectively, you can't just wire them together haphazardly. You need a structural philosophy. AWS provides two massive frameworks that sound similar but serve entirely different audiences. The AWS Well-Architected Framework, or WESNF, and the AWS Cloud Adoption Framework, or CK.
And if you do not keep these two frameworks distinct in your mental model, the exam scenarios will completely tear you apart. They're fundamentally different tools.
Let's start with the AWS Well-Architected Framework. I look at this as the technical blueprint. The WAF is built on 6 pillars: operational excellence, security, reliability, performance efficiency, cost optimization, and sustainability.
The well-architected framework is written for the architects and the engineers. It provides a set of technical design principles and heuristic questions to evaluate your system. When you are staring at a complex Visio diagram of your cloud architecture, the WA is the checklist that tells you if it will survive contact with reality.
I want to deep dive into one specific architectural principle that spans across several of these pillars, particularly reliability because it comes up constantly. Loosely coupled architecture.
Oh, this is vital.
This scenario usually involves breaking a massive, tightly coupled on-premises monolithic application into microservices using tools like Amazon SQS, the Simple Queue service. Why is this such a fundamental shift?
The underlying logic of loose coupling is failure isolation. Let's look at a tightly coupled monolithic e-commerce application. The shopping cart interface, the inventory database query engine, and the third-party payment processing module are all running as a single process on a single giant server.
They are physically intertwined.
Physically intertwined in the same memory space. If the payment processing module hits a bug, consumes all the available RAM, and crashes, the entire application crashes.
So a web interface goes offline. No one can browse products.
The blast radius of a single component failure is total system death.
I like to visualize a tightly coupled monolith like a string of cheap holiday lights wired in series. If one single bulb burns out, the circuit is broken and the entire house goes dark. You have to check every single bulb to find the failure.
That's a perfect analogy.
Right, and microservices with SQS is like wiring those same lights in parallel. The burned out bulb only affects itself, and the electricity keeps flowing to the rest of the system.
That is exactly how the mechanics map out. By decoupling the architecture, you place an SQS queue between the shopping cart interface and the payment processor. They no longer talk directly to each other.
So if the payment service crashes,
The shopping cart interface does not crash. It simply continues to accept user orders and drops those transaction messages into the SQS queue.
so the queue acts as a structural shock absorber.
Yes, the queue holds the messages safely. When the payment service reboots and comes back online, it just reads the backlog of messages from the queue and processes the transactions.
So the user never actually saw an error screen.
Exactly. Their order confirmation was just, delayed by a few minutes. You have isolated the failure, drastically increasing the overall reliability of the system.
And this naturally supports the operational excellence pillar too, right? Because operational excellence focuses on making frequent, small, reversible changes. If you have a monolith, you cannot make a small change. To update the payment module, you have to deploy the entire massive application and pray nothing breaks.
But with microservices, you can update just the payment container independently. The technical pillars of the WAF are deeply interconnected. Building loosely coupled systems improves reliability, enables operational excellence, and allows for granular cost optimization.
Okay, let's set up a role-play scenario here. Let's say my engineering team studies the well-architected framework. They build a flawless, loosely coupled microservice architecture using Fargate and SQS. It scales beautifully.
Sounds like a dream.
But my finance team, who has not evolved their processes, is still demanding a 3-year CapEx forecast for server hardware depreciation before they approve the budget. And my HR department doesn't know how to hire engineers who understand cloud-native design. My brilliant engineering architecture is effectively useless because the surrounding business processes haven't transformed.
And that scenario is exactly why the AWS Cloud Adoption Framework, or CHIF, exists. The forums get incredibly confused by CHI because they try to apply technical answers to it.
But it's not about code.
The Cloud Adoption Framework is not about code. It is about the organization. It is the roadmap for the business leaders, the finance team, human resources, and the executive board.
So WA is how you build the app. CAF is how you transform the business to support the app. Let's break down the perspectives of CAF because the exam tests these heavily.
The CHIF groups its guidance into specific perspectives to address different parts of the organization. Let's start with governance. The governance perspective focuses on cloud financial management, updating IT governance, and tracking business outcomes. It answers the critical executive question: are we actually getting the return on investment we expected from this cloud migration, and are we mitigating risk?
Then there is the people perspective. This is the one that companies always ignore until it's too late.
Oh, 100%.
It focuses on cloud fluency, culture evolution, and organizational alignment. If you take a team of traditional network engineers who have spent 20 years physically plugging cables into Cisco routers, and you suddenly drop them into an AWS VPC environment defined entirely by code, you cannot expect them to thrive without intervention.
The people perspective mandates a structured plan to upskill the workforce and shift the company culture from fear of failure to continuous learning.
We also have the business perspective. This is about utilizing the cloud to gain real-time data insights and accelerate product strategy. It is the philosophical shift from viewing IT as a mandatory cost center to viewing IT as a strategic differentiator in the market.
And finally, the platform perspective. This bridges the business to the technology. It's about establishing the foundational data architecture, the automated CI/CD deployment pipelines, and the internal platform engineering.
It's the business mandate to build paved roads so that developers can move quickly without violating security policies.
And beyond the perspectives, the CF outlines the journey phases of a migration: envision, align, launch, and scale.
Envision is defining the business value, right?
Yes. Align is getting the disparate executive teams, like your hypothetical finance and engineering departments, on the same page. Launch is executing the pilot projects, and scale is expanding those cloud capabilities across the entire enterprise.
Okay, so we have our business alignment via the CF. We have our technical blueprints via the W. The architecture is vetted, But right now, we have an empty house. We need to move the actual enterprise data into AWS.
We have mountains of data.
Exactly. This brings us to the mechanics of global infrastructure. Let's start with getting the data in. I want to talk about the physical transfer mechanisms, the AWS Snow family.
It never fails to shock people that in the modern era of high-speed fiber optics and global satellite networks, the most efficient way to move massive data sets is still to put them on a truck and drive them down the highway.
Let's look at the mathematics behind this. Because there's a scenario where an enterprise needs to migrate like 50 to 75 petabytes of historical data from an on-premises data center to Amazon S3. If you're a junior engineer staring down a 75 petabyte migration, your first instinct is to just upgrade your internet connection.
But the math just destroys that idea.
It absolutely does. Let's say you have a dedicated 10 gigabit per second fiber optic connection. In theory, that sounds incredibly fast.
But network transfers are subject to TCP overhead, packet loss, and latency window scaling issues. Even if you could saturate that 10 Gbps line continuously at maximum theoretical capacity without disrupting any other business traffic, it would take roughly 2 years to transfer 75 petabytes.
2 years?
And in reality, with normal network degradation, it would take half a decade.
Yeah.
Your data would be obsolete before the migration even finished.
So the network itself becomes an insurmountable bottleneck due to the sheer physics of bandwidth. Enter the AWS Snowmobile.
Yes. For multi-petabyte scale, AWS uses the Snowmobile. It is a 45-foot-long, ruggedized shipping container pulled by an 18-wheeler semi-truck.
You're telling me they drive an 18-wheeler to your office?
I am. It is quite literally a mobile data center. AWS drives it to your physical facility, runs dedicated high-speed fiber cables directly into your local network core, and you copy the data locally. Because you are bypassing the long-haul internet, the transfer speeds are massive.
And then what?
Once loaded, they drive the truck back to an AWS region and physically hardwire it into the S3 storage arrays.
Never underestimate the bandwidth of a semi-truck hurtling down the interstate. But what if we aren't moving 75 petabytes? What if we are a mining company operating a remote excavation site with terrible satellite internet generating terabytes of telemetry data a week?
For sub-petabyte scale or disconnected environments, you use the AWS Snowball Edge. This is a ruggedized suitcase-sized device that AWS ships to you via standard couriers like UPS. You plug it into your local network, load the data, and ship it back.
But the edge part of the name is critical, right?
Yes. The Snowball Edge has onboard compute capabilities.
Why would a storage hard drive need compute capabilities?
So you can run local EC2 instances and Lambda functions directly on the device while it sits in your disconnected mining facility.
Oh, wow.
Instead of filling the storage with raw, uncompressed telemetry data, you run a local Lambda function to filter out the noise, aggregate the metrics, and only store the highly valuable anomalies. You process the data at the edge, saving massive amounts of storage space before you ever ship the device back to AWS.
Edge computing in a literal rugged suitcase. Okay, but let's say we do want a permanent network connection. We aren't doing a one-time migration. We need hybrid connectivity. Let's deconstruct connecting an on-premises data center to AWS permanently. We need to clearly distinguish between AWS Storage Gateway and AWS Direct Connect.
The forums constantly mix these up.
All the time.
They solve two completely different architectural problems. Let's start with AWS Storage Gateway. Imagine a media company with an office full of video editors who require sub-millisecond local network access to massive 4K video files.
Okay, heavy local workloads.
However, the local SAN, the storage array in the office closet, is running out of hard drive space. They want to leverage the infinite capacity of Amazon S3, but they cannot tolerate the latency of fetching a video file from the cloud every time an editor scrubs a timeline.
So Storage Gateway acts as a bridge. It's a virtual appliance you deploy on your local VMware or Hyper-V server. The video editors mount it like a standard local network drive.
Exactly.
When they save a file, Storage Gateway caches the active, frequently used files locally on the office hardware for instant access, while quietly and asynchronously syncing the entire massive data set to Amazon S3 in the background. It solves the storage capacity problem by extending the cloud into the local office.
Precisely. It is a hybrid storage solution.
Yeah.
Now contrast that with AWS Direct Connect. Direct Connect has nothing to do with caching files. It solves a networking and routing problem.
Because normally traffic goes over the public internet.
Yes. When your corporate network communicates with AWS normally, the traffic is routed over the public internet. The public internet is subject to unpredictable latency spikes, BGP routing anomalies, and inherent security risks.
I see people ask, why pay for Direct Connect if I already have a 10 gigabit business internet connection?
Because your business internet connection is shared with the world. Direct Connect allows you to establish a dedicated, private, physical fiber optic cross-connect from your data center equipment directly into the AWS backbone network, completely bypassing the public internet provider network.
So it's literally a private fiber line.
It provides consistent, guaranteed network throughput and ultra-low latency. Storage gateways for hybrid storage. Direct Connect is for dedicated private networking.
Now that the data is flowing into the cloud, we must understand the physical layout of AWS itself, the global footprint. The exam heavily tests your understanding of the hierarchy: regions, availability zones, and edge locations.
This is fundamental to designing for high availability. A region, like US East 1 in Northern Virginia or App Northeast 1 in Tokyo, is a physical geographical area in the world. It is not a single data center. It is a cluster of data centers.
And inside that region are the availability zones, or AZs.
Correct. An availability zone consists of one or more discrete physical data centers within that region. Each AZ has its own redundant power grids, independent networking, and separate connectivity. Crucially, availability zones within a region are physically separated from each other by a meaningful distance, usually tens of miles.
Why does the exact physical distance matter? There's a question about how to architect a system to survive a natural disaster.
The distance matters because if a massive localized disaster occurs, a severe flood, a localized earthquake, or catastrophic failure of a regional power substation, it will likely only impact a single availability zone.
Oh, I see.
If you deploy your EC2 instances across multiple availability zones, and one data center goes completely offline due to a flood, your elastic load balancer automatically detects the failure and routes all user traffic to your instances running safely in the other AZ. You survive a physical disaster without manual intervention.
That handles the heavy compute and disaster recovery. But what about edge locations? Because we see questions about serving high-definition video to users globally with minimal latency. If I have a highly available architecture in the Tokyo region and a user in New York tries to load a video, we are bound by the laws of physics.
Yes, the speed of light in fiber optic cables is finite. If the data has to physically travel from Tokyo to New York, the user will experience latency and buffering. This is where edge locations come in. Edge locations are completely separate from regions and AZs. They are much smaller server facilities distributed globally in hundreds of major cities.
And they're utilized primarily by Amazon CloudFront, the AWS Content Delivery Network.
Exactly. When you configure CloudFront, AWS caches a static copy of that video at the edge location situated in New York. When the user in New York clicks play, the video streams from a building a few miles away from them, rather than initiating a request halfway across the globe to Tokyo.
So regions handle the core compute and database workloads. AZs provide fault tolerance. Edge locations accelerate content delivery to the end user.
That's the perfect summary?
All right, we've built the global architecture. We are running decoupled microservices. We have private fiber lines routing our data. Now we enter the final phase. We must become the paranoid operators.
Yes, we have built the mansion. Now we need to lock all the doors, audit the visitors, and balance the checkbook.
We are diving into security, governance, and cost tracking.
This is where the day-to-day operational reality of managing a cloud environment lives. And the absolute foundation of operational security in AWS is IAM identity and access management.
The core philosophy of IAM is the principle of least privilege. Give us the mechanics of this.
The principle of least privilege dictates that you grant a human user or machine role only the exact minimal permissions required to execute their specific task, and absolutely nothing more.
So no blank checks.
None. If a developer needs to read log files from a specific S3 bucket to debug an application, you write an IAM policy that grants them S3 get object access exclusively to that single bucket Amazon resource name. You do not give them full S3 access. You certainly do not give them administrator access.
Because if that developer's laptop is compromised by malware, the blast radius of what the attacker can achieve is strictly confined by that IAM policy. They can read the logs, but they cannot delete the databases.
Exactly.
This leads directly to the most critical security rule in AWS, the AWS root user. The root user is the original email address and password you used to create the account. It possesses irrevocable God mode access. I see people ask, why can't I just put a hardware MFA token on the root user and use it for my daily admin tasks? It seems simpler than managing multiple IAM roles.
It seems simpler until you make a single mistake. The forum consensus is absolutely correct on this one. Never use the root user for daily administrative tasks.
What's the protocol then?
When you open a new AWS account, your very first action must be to enable multi-factor authentication on the root user. Your second action is to use the root user to create a separate IAM user or role with administrator privileges. You then log out of the root user, lock those credentials in a physical vault, and use the IAM admin for your daily operations.
Why the separation? If both have admin privileges, what is the difference?
The difference is revocability. If your IAM admin user's credentials are leaked on GitHub, you can log in with the root user, delete the compromised IAM user, and stop the attack instantly.
But if the root user is compromised...
If your root user credentials are compromised, the attacker can change the root password, lock you out entirely, and you lose the entire AWS account and the business that runs on it. The blast radius is total.
That is terrifying. And for programmatic access, when an application needs to interact with the AWS API, you don't embed passwords in code. You use access keys.
Yes. Passwords are for human beings logging into the AWS Management Console via a web browser.
Yeah.
Access keys, which consist of an access key ID and a secret access key, are long-term credentials specifically designed for automated scripts and applications making programmatic API calls.
Okay, the doors are locked, the blast radius is minimized. Now let's balance the checkbook. Following the money is a critical operational skill. We need to contrast AWS Cost Explorer with AWS budgets. I found this brilliant memory hook in the forum discussions. Someone wrote, "To explore is to visualize, to budget is to alert."
I saw that comment, and it is a fantastic heuristic for your exam. Let's expand on the mechanics of each tool. AWS Cost Explorer is an analytical rearview mirror tool.
Looking backwards.
Yes. It allows you to look backward at your historical billing data, visualize your spending trends with granular graphs, filter by tags, and forecast what your bill might look like next month based on past behavior. It is designed to help you conduct an autopsy on your bill. It answers the question, why did my EC2 cost spike by 30% in November?
But Cost Explorer will not physically stop you from spending the money. It just helps you understand the damage after the fact.
Exactly. Cost Explorer is for analysis. AWS Budgets is a proactive control mechanism. You use budgets to set custom, predefined thresholds.
Like an alarm system.
Yes. You configure a rule that states, if my forecasted spending on RDS databases exceeds $500 this month, immediately send an alert to the engineering Slack channel and page the on-call manager. AWS Budgets is the radar detector that warns you before you run out of money.
To explore is to visualize. To budget is to alert. And while we are on the topic of cost, let's talk about automated right-sizing. We mentioned it earlier during the elasticity discussion, but there is a specific ML-driven tool for it, AWS Compute Optimizer.
Compute Optimizer is an incredibly powerful tool for cost reduction. It utilizes machine learning algorithms to continuously analyze the historical CloudWatch utilization metrics of your running EC2 instances, auto-scaling groups, and EBS volumes.
So it's looking at what you're actually using versus what you provisioned.
Right. If an engineer provisioned a massive instance with 32 CPU cores, but Compute Optimizer analyzes the telemetry and sees the CPU utilization has never exceeded 5% over the last 2 weeks, it will explicitly flag that instance as over-provisioned.
Oh, wow.
It will literally recommend a specific smaller instance family that meets your performance needs while saving you money.
It takes the guesswork out of right-sizing. It's like having an automated financial auditor reviewing your infrastructure decisions.
Finally, we must discuss what I call the all-seeing eyes of the AWS account. I want to clearly contrast AWS Trusted Advisor and AWS CloudTrail.
Two very different, very important tools.
Trusted Advisor acts like an automated high-level management consultant constantly scanning your entire AWS account configuration, right? Yes. It evaluates your current setup against established AWS best practices across 5 core categories: cost optimization, performance, security, fault tolerance, and service limits. It provides a dashboard with actionable real-time guidance.
So it will tell you if you left a door open.
It will literally highlight, you have an unattached elastic block store volume that is costing you $50 a month, or you have a security group that is dangerously open to the entire internet on port 22. It tells you what you are currently doing wrong.
So Trusted Advisor evaluates the current state of your architecture. But what about AWS CloudTrail? There's an operational nightmare scenario. An EC2 instance critical for the development team is suddenly inaccessible, and upon logging into the console, you realize the instance has been completely terminated and deleted. Who deleted the instance?
That is the exact scenario CloudTrail was engineered to solve. AWS CloudTrail is a comprehensive auditing service that records every single API call made within your AWS account.
And in AWS, everything is an API call.
Everything. Whether a human clicked a button in the web console, a Python script executed a command, or an automated CloudFormation deployment triggered a change, every single action is logged. CloudTrail records the identity of who made the request, the source IP address, the exact millisecond the request was made, and the specific resources that were affected. It is the ultimate security and compliance audit log.
It's the security camera system of your AWS account. If an instance vanishes, you don't guess. You query the CloudTrail logs, filter for the terminate instances API event, and it hands you the exact IAM user credentials that issued the command. Case closed.
Trusted Advisor is the consultant telling you how to improve your posture. CloudTrail is the auditor recording exactly what happened in the past.
We have covered a massive amount of architectural ground today. We started by dismantling the legacy IT mindset and understanding the economic shift of CapEx to OpEx.
We navigated the treacherous compliance waters of the Shared Responsibility Model.
We completely deconstructed the underlying mathematics of compute pricing, mapped out the operational boundaries between the WAF and CF frameworks. We drove a 45-foot truck full of data to bypass TCP overhead.
And finally, we locked down the account with strict IAM policies and CloudTrail auditing.
It is a comprehensive journey, and it really highlights why memorizing flashcards is fundamentally insufficient. The CLF-C02 is not a vocabulary test.
Not at all.
I want to reiterate this to you, the listener. The Cloud Practitioner exam is a mindset test. Understanding the technical mechanisms behind elasticity versus the business capability of agility, or knowing why your engineers use the WAF while your executives need the CF. That is what separates a truly certified cloud practitioner from a forum-scrolling guesser.
The flashcards won't save you when production goes down. You have to understand the muddy waters of the architecture itself.
Exactly. I want to leave you with a final provocative thought to mull over as you continue your cloud journey.
Let's hear it.
We've talked extensively about how cloud computing is a spectrum of abstraction. We are moving away from raw EC2 servers, where you're burdened with managing the operating system, towards serverless architectures like Fargate and Lambda, where AWS manages almost everything beneath your application code. As this evolution accelerates, how long will it be until the shared responsibility model shifts so entirely to AWS's side that developers entering the workforce no longer need to know what an operating system even is?
That's a profound thought. The cloud is evolving so rapidly that passing this exam is really just step one in a lifelong journey of unlearning the old ways of IT. The foundational knowledge you build today is what will allow you to adapt to the abstractions of tomorrow.
Thank you so much for joining us on this deep dive. Keep building, keep questioning the defaults, and we will see you next time.